So Laura, can you share your screen?
Yes. Can you see my screen?
Yes, we can see you. So Laura Bernard is from CNRS France, and she will be talking today about analytical modeling of gravitational waves beyond general relativity. So over to you, Laura.
Okay, so thank you very much. Thank you for the invitation. Yes, let me start. So first, I will do a quick introduction because Raphael already did a broad introduction. So I just wanted to add that we are now discovering and observing many gravitational waves, but we still have a lot of things to learn about it, and there is a lot of unknown. So I put just here as an example the latest official gravitational wave observation. So the first one that was published for 04, which is GW 230529, and in which the primary black hole is in the in this gap, so the low mass gap. And we don't know yet, for example, what is the nature of this object, and so this is something we need still to understand better. And one way to do it is perhaps with a more accurate modeling or a more better understanding of neutron star physics, for example, or these kind of things. So there is still a lot of things to learn with gravitational waves. Actually, it's only the beginning of the gravitational wave science. But to this, so of course, as it was already mentioned, we need so the data we received is very noisy, and it's very difficult to detect and to estimate the parameters. And for that, we need very accurate waveforms. So this is just an example of the signal you get and the waveform you need to find into it, based on one of the first detection. So I will go quickly on the following. You know that because it was already explained by Raphael, but to model very accurately gravitational waveform, we need to use different methods and techniques, because the regime of validity of each technique is focused only on a small part of the parameter space. So if you do the traditional plot comparing compactness and mass ratio, so compactness is more or less the gravitational strength, and mass ratio is the mass ratio. You see that on the right part of the plot, you have extreme mass ratio, and so this is tackled by gravitational self-force formalism, which I want to speak about. So it's an expansion in small mass ratio. But then when you go on the left part, on the top part, you have slowly moving objects. And in that case, it's post-Newtonian formalism that can use it. So an expansion for small velocity, small gravitational field. So this is valid in principle for any mass ratio, but in practice for high mass ratios, gravitational field will become stronger. And so post-Newtonian formalism doesn't work as well. And then when you go on the bottom left part of the plot, you have highly relativistic, so very strong gravitational field, strongly moving. So the two objects become closer and closer. And so in that case, you need to resort to numerical relativity tools. So you need to solve the full Einstein equation. And this we only know, as they are highly nonlinear, we only know how to do it numerically. But numerical evolution is very expensive, computationally expensive, and so you can only do it for comparable mass ratio, and it's very difficult to do it for high mass ratio. So that's why it's stay on the left. And then, of course, to get the full waveform, you need to map all this formalism to get the full in-spiral merger Meudon, and this is done currently with 2 or 3 methods. So in effective one-body and phenomenological models mostly are the one used, and also some surrogate model based on numerical relativity templates. And finally, it was already mentioned extensively by Raphael that there are new methods coming into the game, among which scattering amplitudes, that it does an expansion in post-Minkowskian, so any velocities, which is orthogonal to post-Newtonian expansion. And also more recently, a study of asymptotic symmetries, so asymptotic symmetries at infinity, that can be mapped also with the post-Newtonian formalism and the waveform computed in that case. So in my talk, I will focus mostly on post-Newtonian formalism and traditional methods. So post-Newtonian formalism, it was already mentioned by Raphael. There are many methods to tackle them. The first one and the original one was what I would call traditional PN, but it's just because we need to give it a name. In practice, it's account to solve directly solve the Einstein field equation in the phase space, in the Dirac space. So not going to Fourier space, and so we just solve some D'Alembert equation directly. So I will explain more how it works in the following. But more recently, in the past 10, 20 years now, there have been new methods coming from more particle physics, theoretical physics people, and that are very efficient when applied to gravitational theory. It's based on effective field theory, so it's a diagrammatic approach, and integration is done in Fourier space. And so Raphael explained how efficient it can be, and it can also be applied to not only to post-Newtonian, but also to scattering amplitudes, doing a PM expansion. And so this scattering amplitude, so you can use effective field theory, but you can use also more over method that I won't mention. I think it will be mentioned maybe later, but I'm not expert. And so this is, so I won't come back on it, saying that these two methods, PM and PN expansion, are orthogonal, and we can learn things in the PN expansion that is used for the waveform by using result from PM expansion. So for example, you see that if you get the 4 PM result, you get the full 3 PM result, but only a partial one at higher PN on. Yes, and so that's it. And so in the following, I will focus on what I call traditional PN method, so direct integration of the field equation, and I will show how it works in GR, but then I will show how we can extend it to alternative theories of gravity. So let me start, as usual, by the Einstein field equation. So you have the Einstein tensor on the left, and the source term, the matter stress and energy tensor on the right. If you define the perturbation, which is not only a perturbation like this, so the deviation from Minkowski of what we call Gotti metric, so this metric density, you can rewrite the field equation in an exact matter by this way, with a flat D'Alembertian on the left, some matter field on the right, plus all the nonlinearities. So this is an exact formulation in principle, provided by all the nonlinearities are in this lambda mu. It is very nice because you have the flat D'Alembertian, so it's a well-posed wave equation. We know how to solve it, and we can evolve it also. So this was the result by von Schockenbrugger. Then it will determine this is the equation we solve, and when we solve it, it will determine the value of h mu for certain distribution of matter, because we have the source, and I already said this. And then we need to, as we are in GR, we need to impose some gauge condition, and we impose the harmonic gauge condition by this divergence of h mu being 0. And in that case, it will also correspond to it's equivalent to the matter conservation equation, so how the matter is moving. And in practice, we can either impose it by hand when we solve iteratively at each order, or we can include it by keeping this term here that contains only, that is proportional to this divergence. And if we keep it in the Einstein equation when solving, then at the end, we will be sure to be in the harmonic cage. So that's what we need to solve. And so to solve this equation, we just need to take the inverse of the D'Alembert operator that we have here. So in principle, it's very easy. We know the green function for it. And so we take the retarded solution, so solution in the past, like over the past, like integration over the past icon. So this is done by this expansion here. And so, yeah, well, it seems very simple because we are in flat space, so we know this. But in practice, it's a bit more complicated because we have to solve this, and we have the retarded operator. So we do it by separate different zones. So first, when we are close to the source, we can do this kind of expansion around T, because we are in close to the source, so this is close to 0, and in that case it directly give an expansion in power of C or B over C. So that's where the Pn expansion come from directly, you can see it. But there is a problem, is that when you go away, so for large R, we see that the expansion becomes ill-behaved, and so we cannot trust on it. Also, it's also valid close to the source, so we don't have information about boundary condition at infinity, and so if we just do this, we won't have information, for example, about the tail. So we'll have to solve this problem at some point. Then we can do the same, but in the wave zone, so outside, far from the source. In that case, we end up with a multipolar expansion, but again, it's ill-behaved close to the source, so when R goes to 0. So in practice, we will combine the two solutions. So the one that is close to the source, that solves the motion of the source, which is in orange here, and diverge at infinity, with the one that solves for the propagation of the gravitational wave in blue here, that diverge near to 0. And then if we match the two solutions in smart way, we can end up with a regular solution everywhere that contain information about the source and what happened at infinity. Let me just give a bit more detail on each of these solutions, starting with the solution in the exterior. So in the outside of the source. So in that case, we solve the Einstein equation in vacuum. So we only have the nonlinearities and no information about the source. And we can do it by using a multipolar solution, so introducing some multiple moments. And so we can do it at first order, so in power of G, and then iteratively at higher and higher order, and we end up to the full solution, which is the sum over the power of G of a solution that depends on a set of multiple moments. We have the two source moments, so current mass one and current one, plus some gauge moment that comes from the gauge. So this is the most general solution outside of the source. Of course, for the moment, we are solving in vacuum, so we don't have any information about the source. So this will be fixed later. We can then look at the behavior of the asymptotic behavior of the source. We have seen that it diverges near 0, but also it has at infinity, future null infinity, it has a behavior in log R over R, but we want a behavior in 1 over R. And so this is an artifact of the harmonic gauge, and we know that we should be able to find a radiative gauge where at infinity, future null infinity, the solution behaves as 1 over R. And so this is done by going to null coordinates, which are kind of boundary coordinates. And it's just we incorporate the logarithmic divergence in this null coordinates. And when you do this, you can see that the solution at infinity behaves 1 over big R, which is exactly what we want. And in that case, the solution now depends on two sets of mass of moment, the mass and current still, but can be linked to the source moments, like this, where the correction to the second time derivative of the mass moment, for example, contain nonlinear correction in higher power of G, and in particular tails, memory, etc. Now, looking at the near zone, so close to the source, we have we do a Poissonian expansion, so in power of 1/c. So this is just solving the flat D'Alembert with a source term, no, plus also the nonlinearities. We do it iteratively in power 1/c. So we have the same solution, the flat, the inverse, the retarded green function in 1/r. But the problem is that we will have to integrate over all space the source, and the source will, because of this, so the source here is compact, so in part this is easy to treat, but it will contain at higher order nonlinearities, so term that contains a solution at lower Pn order, but that is valid in all space and that can diverge. And so we don't know how to solve this, and it will give some divergences in the integration we have to do. And also we don't have, in this way, as I said, we don't know how to incorporate information about the boundary condition at external infinity. So the way to solve both problems, so the first one is to use some regularization procedure. And so the regularization that is now used is dimensional regularization, which is the same that other people with other methods, either the Hamiltonian, ADM, or the EFT technique used. It's dimensional regularization. It comes from EFT techniques. It's very efficient. So this is now settled. And the other question, the way to answer it, it's to rely to some asymptotic matching. By matching the two solutions, the exterior one and the near zone one, we will get information about it. So what is the matching? It's saying that in a small region, the buffer region, there is an overlapping between the near zone and the weight zone. And in that case, the two solutions should coincide. And if we re-expand each solution where it diverges, then we can formally say that the solutions are the same, but the same formal way. And so doing so, you can obtain information first about the source multiple moment, what is their expression as a function of the source. We give the information about the source, the matter source, in those exterior wave zone region. So this is this, and it's a traditional result, for example, for the quadruple moment, which is an integration of the source, and that gives m times x1 yj, let's say. But it gives a classical quadruple moments, and you have the same for the current moment. And at the same time, it will give the information about what's happened at infinity in the near zone solution for the tail, for example. And so, for example, in the dynamics, so in the conservative solution, we have this nonlinear radiation reaction effects that comes from the interaction between the mass, the curvature of space-time, and the quadruple moment of the gravitational wave emitted, that will back react and go back to the source at a later time. And so this effect starts at 4 p.m. And so it should be incorporated. And this is the correct way to do it. So when we do all this procedure, you get the full solution. So first, the conservative dynamics, then which give you for example, the energy, and then also the dissipative part in the energy. And it gives you also once you have computed all these multiple moments, it gives you the gravitational wave field at infinity, which behaves as 1/r as we want. And if you combine everything from this, you can get the flux at infinity, and writing the energy balance, so the dissipative energy, the energy dissipated by the source, and you with the flux received at infinity. Using this equation, you can get all the quantities, the evolution of the quantity related either to the dynamics, like the decay of the orbital period, the eccentricity, etc., and also the various gravitational wave modes, so the amplitude, the phase, etc., that are used by the gravitational detector, for example, to get to analyze the data. So this has been done in GR with high precision. It has been done for the dynamics first, also including spin. So spin effects are added in an effective way by adding some finite size effect feature to the point particle action we started with, when in the case of non-spinning effects. And so it can be computed. It has been computed with at a high precision also with EFT techniques or traditional PN techniques. And the non-spinning case, which is also is known at full 4PN result, and also with some partial result at higher PN order. So 4.5 in the center of mass frame, for example, and 5PN, there are some result, but also some discrepancy still due to treatment of tails and this kind of effects. So this has still to be understood. For the flux, it's the same. So the only thing is that in the dissipative case, EFT technique can also do it at a high order in principle, but it has not been done. So it's the very high order are mostly done with traditional PN techniques. And so the most recent result is the 4PN beyond the leading order term. So this red term here, flux and gravitational wave mode and the phase also that were computed very recently. And also the spin have been computed, and I didn't mention, but tides. And then the result for the dynamics, it's for any orbit, but when you go to the waveform, you need to do an assumption in which is usually the quasi-circular orbits. And there are some results for small eccentricity and expansion in the small eccentricity up to 4PN, but only for small eccentricity. And then some people that computed this 4PN flux, and in particular David Festini, they give the estimate of how much it improves the waveform in terms of number of cycles by adding a PN order. And you can see that apparently depending on the sensibility and the source you have, so for LIGO, Virgo, ET, or LISA, you need some precision on the phase of the cumulative phase, number of cycles you can see. And you see that adding 4PN, for example, it's for LIGO, Virgo, it gives 0.1 cycle precision, which is more or less what is needed to do a good parameter estimation, but probably for LISA and ET, it is not sure that it will be sufficient, but it is still to be discussed, let's say. And to conclude on GR, let me say a few words about 5PN. So current results have been obtained by a combination of different techniques, and mostly techniques from EFT, which gets the binding energies, gravitational potential, some result on hereditary terms, although there are some discrepancies yet. Result coming from scattering amplitude techniques that I mentioned, and also some result from cell force expansion in small mass ratio that can give information on the corresponding coefficient in the PN expansion. And so by combining these methods, we can hope to have a full 5PN result like this. Doing the full computation only with traditional techniques might be a bit difficult, or at least very long. So that's it for this part. Let me now go beyond GR and show how this can be adapted to other kind of theories. So for this talk, I will focus only on scalar tensor theories, so theories that add an additional scalar field. As you all know, GR is a beautiful theory that works very well and that has not been challenged so far. So one question would be why we don't see any deviation. So this is, for example, the result, the most recent result that I could find from LIGO Virgo on test of GR, and you can see that it agrees very well with GR. So they modify the PN coefficient for the phase at each p-n order separately, and they obtain a good agreement with a 0 deviation. So you see that the best constraints still come from the -1 p-n term, which is a dipolar radiation. So we don't see any dipolar radiation, basically. So well, then I can either stop here or continue. So if I continue, let me explain why I continue to speak and why do we want to modify GR. So one reason that is not written here is simply also because we want to understand better GR and gravitational theory, and one way to do it is also to see what happens when we modify it and when we consider different theory. But then if you want more phenomenological reason is first in the high energy regime, we know that GR is not renormalizable and we want a quantum completion of GR. So some alternative theories try to solve this problem. Other theories look at the other regime, low energy regimes, cosmological scales, and they tend to give an explanation for the dark sectors, like dark energy. So why a cosmological constant can be just an artifact of modified gravity theory. And dark matter. So is it a new type of matter that has not been observed so far? Or again, can it be explained by modifying our theory of gravity? So to modify gravity, we need to modify GR, but GR is a very solid, strong theory that is difficult to modify. So to modify it, we need to relax some of the assumption. And so in particular, we can either add additional fields or give a mass to the graviton. We can also relax Lorentz invariance. So go for a theory that violates Lorentz invariance. This is done, for example, in Orjava-Lipschitz theories that are potential quantum completion of GR. And we can also leave the 4th dimension and go to higher dimensions, like Kaluza-Klein theories. So I will focus, and so if you do this, of course, well, you end up with a full zoo of theory that is explained here. And it's very difficult to study some of them. You need to put some constraint based on first observation, and then on also some well-behaved fundamentally, number of degrees of freedom, etc. No ghost, all these kind of things, which can reduce the number of theories, but you still end up with a lot of theories. So in my case, I will just focus on the class of scalar tensor theories, because it's the simplest thing you can do, just add one scalar field, massless. And in that case, if you want, you can still want to write the more general Lagrangian that you can write with one additional scalar field and only second order field equation. And you end up with Ondinsky type of theories, which are very kind of complicated because you have all of these possible terms. Then you can add some additional constraints. So the first one is that you don't have fifth force, so you need a screening mechanism to screen the fifth force due to the scalar field. So in some theories, it's done naturally because this fifth force will appear as a small correction, so the leading term will still be the gravitational potential, but in other theories, it doesn't work like this. So this is the first constraint. Then, as you know, with some gravitational wave, we have observed that they travel at the speed of light. And so if you apply this, it can give reduce the theory to this Lagrangian only, which is with the G2, G3 basically modification. But still it's debatable because it's a constraint that applies to cosmology, but not if you consider that your theory, for example, is a theory to explain modification of GR at high energy only. And finally, a very important theory, if you want to do prediction with your theory, and so in particular to get gravitational wave and to get numerical simulation from it, it's that the theory is well posed with a well-posed formulation. It obeys to the Cauchy problem. And so it was shown, for example, from Banzdiki-like theory by Ivan Shukeboya again in harmonic coordinates. So the game is usually to find a gauge in which the theory is well posed. And more recently, it has been studied a lot after work by Pretorius, Ripley, Papalo, and Real, for example, showing that finally this theory can be made in a weakly hyperbolic if you introduce a modified harmonic gauge. And since then, there have been a lot of study of it and also numerical simulation in those theories. But if you want to impose strong hyperbolicity, usually you end up with a much restricted theory. Let me show you an example of how it works. So considering what I call a still too complicated theory, it's just what K-sense theory, so theory that has the Ricci scalar plus a kinetic term that is non-canonical for the scalar field. So I forgot to say it, but X is a kinetic term for the scalar field. So d phi, d phi. And so if you expand it, you can get higher order, so d phi to the so x squared, x third, etc. And if you write the field equation for this theory, you get these two field equations. So the gravitational one for the metric, which is the traditional one with some correction that depends only on the first derivative of phi, so d phi. So this is very well, and we know that we can put it going to harmonic gauge into a flat D'Alembert operator, and we can solve it, and it obeys the Cauchy problem. Everything is fine. But the scalar field is more complicated because it has this form. And in principle, we cannot expand this because it depends on the strength of this x, basically. And this term here, and if you're in a perturbative regime, this can be small, and in that case, you can again put your equation as a flat D'Alembertian. We know how to solve it, but in some case, in particular, if you want to screen the fifth force, so if you have this x squared or x to the 3 term, then this can grow, this k prime here, and we cannot expand it, and it will give some term, and we cannot really do a Pn expansion as we do, and we don't know the green function to solve this equation, so we need to find a way, and this is not, there have been some attempts, but it's not a solved problem yet. And so that's why to get gravitational waveform beyond GR, we still need to go to a simpler theory, which is Bronsdeki-like theory, so canonical kinetic term, plus some coupling. So here it's in the ancient frame, so I do the coupling through the metric to the matter, and I don't put it in the gravitational sector. But in practice, we can go from one frame to the other, it doesn't matter. So this is easier to do the computation. So in that case, the field equations are very simple and are the same as in GR. So you have exactly the same as in GR, but with some correction due to the scalar field, and you have the scalar field equation that has exactly the same form. So we will be able to expand it, Pn expand it as previously, as for the metric, and in particular, phi will behave more or less as H00. So let's do it. Yeah, that's what I said. And let me note that I'm studying this theory, which is very simple. It's probably very much constrained also by binary pulsar observations. So it's probably not the ultimate theory, but it's a good starting point to study more complicated theory like Einstein scalar Gauss-Bonnet or over theory. And so, yes, we need to start somewhere. So let's start with this. It has also a Noether theorem, so black holes in this theory are the same as in GR. This is not true for this over theory, but in this case, yes, but neutron star can be scalarized, and so we will, as soon as there will be one neutron star in the binary system, we expect to see deviation from GR. When we do this theory of going beyond GR, we need to find a way to describe our compact object to squaraturize like the point particle description. And one way to do it is to do a point particle description, but with a mass that depends on the scalar field. So that will describe how the mass will react to this additional field. And to know exactly what is the value of this mass as a function of scalar field, we need to know some analytical solution or numerical, but better analytical solution, either for black holes. So if you know analytical black hole solution, that will be different from GR. So I'm speaking of any theory. In that case, it will give you the exact formulation for this mass as a function of scalar field. So this was done, for example, in Einstein-Maxwell dilaton and Einstein scalar Gauss-Bonnet by Félix Louis-Joliet. And if you look at neutron stars, for example, in the theory I'm considering, then you need to solve the equation again. It will depend a bit on the equation of state, but you will show that how it behaves. And if you define like the sensitivity, so related to the scalar charge, you can show that it gives some value for the sensitivity around 0.2 for neutron stars. So there will be a deviation. So once you have done this, you have a description for the matter. So in principle, it's a point particle description, but then you can again add spins and tidal effects. And if you do this, you can compute the full PN result. It was done. And I will just highlight the main difference compared to GR. So the main one is that the radiation reaction effect, so the dissipative effect in the equation of motion, start at 1.5 PN. Contrary to GR, where it was 2.5 PN. Also, there is this tail term that I've mentioned before in GR that started in 4 PN, which is the non-local term, so integral over the path of the source, again, like Raphael mentioned it also. And in that case, it's due to the dipole moment, an interaction between the mass and the dipole. And so it starts only at 3 PN order. And finally, we have also tidal effects, so deformation, and there is a tidal effect due to the scalar dipole moments that we have. And this effect will start at 3 PN only, while it was the traditional tidal effects, gravitational tidal effects, start only at 5 PN. So these are the main results that are known and that were computed in the equation of motion. So just to explain a bit more the tail effect, so it's for the equation of motion, it's an interaction in that case between the mass and the dipole moment of the source. So this is the gravitational wave emitted that will back react on the curvature of space-time and go back to the source. And this is this path here and give you a contribution. If you look at the flux, so at the gravitational wave emitted at infinity, again, you have everything that starts at -1 PN order. So you have the traditional GR term that is here in black, plus some correction due to the scalar field, and that starts at -1 PN order, which is what I've highlighted here by putting x, where x is the Poissonian parameter, 1 versus square, to the power -1, and you have some correction. And there are different important things. One is that there is a scalar tail term that starts at 0.5 PN that was absent in GR because this is due again to scalar dipole moment, so it starts earlier than GR. You also have a new scalar memory term that contributes to the quadrupole moment, the mass quadrupole moment here, so it will give contribution in the gravitational flux. And that is the interaction between the two scalar dipole moments. And finally, you also have the scalar tidal contribution that starts earlier. And so for the tails, this tail term here, just to show you on my plot, that's again mass time dipole interaction, but in that case, it will follow this path. And so interact at the point of space-time where I'm observing my gravitational wave. And so those results have been used by people compared to results from obtained numerically with numerical simulation by people in Caltech, Susan Ma in particular. And so you can see that there is a good agreement between PN result in pink, purple, and numerical result in green here. So of course, at the end, close to the merger, it's not good agreement because PN is not valid anymore, but at the beginning, it's kind of a good agreement. Now, before finishing, I want to just speak a bit more about tides, how to add them, because we have seen that they are starting at earlier PN results, so it's important. It could be a good way to distinguish or to put more constraint on the theory, very strong constraint on the theory by looking at them. So they come from the fact that we have now a varying scalar dipole moment that will give a response, that the compact object will respond to this external scalar dipole a moment, and the way it responds, if we use as in GR an adiabatic approximation, saying that the response of the body, the scalar dipole, let's say how the body will be modified, is proportional to the external field by a coefficient of proportionality that will correspond to the love number or the coupling parameter in the FT action. And so if you introduce a dimensionless scalar tidal formability, because this has a dimension of length square, so if you put it, make it dimensionless, then you can see that in the field equation, for example, the acceleration, it gives at leading order a 3 PN correction and not a 5 PN. And so if you want to reach 5 PN, you can write it in the action in an effective way by adding correction to the point particle action. So you have the first term here that gives a 3 PN correction that depends on the scalar dipole moment. Then you have a term with second order derivative of scalar field. You have in green here the term, so these are the purely scalar tidal deformability parameter, lambda mu. You have the gravitational, electric, and magnetic type love number that comes from this term that is present in GR. And then you can have also some coupling between scalar tide and gravitational, so which are this term here, which we call gravitoscalar tidal parameters. And so all these, so the first one gives a 3 PN correction at leading order. It will give some contribution also at 4 PN. And then all these new terms, nu, and c, will give correction at 5 PN for the first time. And so this has been computed in the equation of motion and is currently being computed at for the flux. And so people like Gaston Cressy in particular in the Netherlands have been trying to compute the value of this coupling parameter, mu, c here, and see what could be the value. So these are a sample of the result here. So on the top left, you have the result for the gravitational quadruple moment parameter, log number, let's say. So in straight line is the result for GR, and in dashed line are the results for some scalar tensor theory. And you see that it can be quite different from GR, depending on some parameter of the theory. But then you have also the moments that are absent in GR. So on the top, on the right, you have the scalar type log number, and you can see that the value is not zero, so it can be important. So it's good to have them. And no, sorry. So on the right, it's the gravitoscalar. So the coupling between scalar and gravitational tensor tidal interaction, and the bottom left is the purely scalar sector. And they can be quite big because you see the value are quite high. And so just to show you the result we get, for example, a small sample of the result for the Lagrangian, so binding energy at next to leading order is like this, and this is that correspond only to these 3 diagrams, but we have much more, so the result, again, as in PN, is always very big. and I'm not showing it more. And finally, before concluding, let me just show how this result is important and can be used to study other theories. So the first thing you can do is to have a massive scalar field. So this is very nice. You add the potential, for example, for the scalar field. And so by doing this, you will have a Yukawa decay. So the scalar field will quickly decay depending on the mass of the scalar field. There have been some results at 1p order, in particular using EFT techniques, but the problem is that if you want to get, you have to get the result with hypergeometric function. And if you want to go beyond this, it's very difficult to solve the equation, and you need to expand in particular with in small mass. Then you can have multiple scalar fields. So it has also been done originally by Tamura and Esposito Fares, and then by Shon and Doneva, for example, for the dynamics and the flux at a lower order. So this is very simple. It doesn't have much restriction compared to previous results. It's just a simple generalization, let's say. Then you can also add a Maxwell field. So this is what is done usually in ancient Maxwell dilaton, for example, theories. So in that case, you add the kinetic term for this Maxwell field, but here is massless, and you have some coupling with the scalar field. And in that case, the tricky part is the description of the skeleton your action, because it will depend on this Maxwell field. And so it was done by Félix Louis Julier, and he showed that the electric charge has to be constant, and so as the mass, by matching to non-solution, you can obtain the mass as this function of the electric charge and the scalar field. And so this will give all the sensitivities in particular. And then he computed the dynamics and the flux at 1p order, which is very similar to the simple scalar tensor theory, but you need to modify some parameter to include this electric charge. Then maybe more interestingly, you can add coupling to curvature term. So this is done has been studied in very detailed in these two theories, in ancient scalar Gauss-Bonnet and Chern-Simons gravity, where you coupled the scalar field for this function to either the Gauss-Bonnet invariant or to this density for the Chern-Simons. So in Chern-Simons, this is a theory that is studied for quantum gravity and that violates gravity. And so what is interesting with those theories is that they have black holes that are different from GR, and so we can opt to see deviation in that case, and in particular for spinning solution are different from GR in Chern-Simons. So they have been studied mostly for the spin correction in this case. But if we look at, for example, ancient Gauss-Bonnet, you can see that when we add this term here, again, the coupling constant as a parameter of length square. And so we can show that the correction in the theory also is formally a 1/c square, so 1pn correction to the dynamics, for example. If you make this coupling constant dimensionless, as what happened for the tidal effects, it will formally be a 3pn correction. And so as we get already the full result from simple scalar tensor theory at 3pn, we just need the leading order correction due to the Gauss-Bonnet term to get the full result in this theory at 3pn. So this was done for the dynamics, the flux at a lower order, and also for the leading order tidal effects. Leading order correction due to this term in tidal effects. So depending on how we define, there are some different results, but you can map them. And you can see that the way all these love number there is a degeneracy between the different type of love number depending on how you couple it to matter. So that's it. So just to conclude, I wanted to say that there is still a lot to be studied in this theory in order to have waveform that are completely too complete for the next generation of gravitational wave detectors. And there have been a lot of work on it using many different techniques nowadays, and in particular techniques from scattering amplitudes that can be also applied to modified gravity theories. And we can do it, for example, for scalar tensor theory, where there have been some recent result by Talman chain, for example. One thing that is very important for the future is to add also these non-perturbative effects like spin, dynamical tide that are known and starting to be very well included in the waveform in GR, but have also to be included beyond GR. I've only shown results for a simple theory, scalar tensor. It's good. Of course, we won't be able to have a waveform in all the different theories that exist, but we need to probably have a good sample of theories with different kind of phenomenology, like theories that violate Lorentz invariance or theory of massive graviton. It would be interesting to see what could be the exact gravitational wave prediction for this theory, to have full waveform and precise waveform. So this is a lot of work for the future. So I'm stopping it, and so thank you.
Thanks, Laura, for the great talk and finishing on time. So we have time for a few questions. So please go ahead and raise your hand. I think we have a question in chat. So I can read it out. In the beyond GR models, why can you model gravitational wave further than classical PN calculations? On your comparison plot, we can see a merger in beyond GR modeling, not in PN.
You mean on this? Sorry. On this plot. It's because the result it's not a it's just a comparison between numerical relativity results and PN results. So PN results are valid up to some point, and then it stopped being valid because we are too close to the merger, and so the gravitational field is too strong, and so the approximation is not valid anymore. So that's why the PN waveforms stop at some point, and you have some discrepancy. While the green curve is, so they call it ST for scalar tensor, but actually it's numerical relativity waveform for scalar tensor theories. And so it's done to have the merger, so it's really done for this, and then they can have a few cycles before the merger, but not many. And so they compare to the cycle they have with their numerical relativity results with the result from the PN by matching at some point and see how it agrees up to where. But of course, in principle, so the green curve, it has the merger, and it has a few cycles before the merger, but it doesn't have many cycles, while the PN curve that you see here, in principle, you can extend it to the left for very large, like tens of thousands of cycles. And so that's why PN waveforms are still very useful, and in particular for the next generation of detectors like LISA or Einstein telescope that will be able to see many cycles before the merger.
Okay, any further questions? While we wait for next question, I had a very short clarification for Laura. So you mentioned that in the scalar tensor theory, the tidal effect comes at a lower PN order in comparison to GR. So if to understand that physically, when we have GR, we understand the tidal effect coming at a later time of the in spiral, because two bodies need to be close to each other for the tidal effect to kick in. So in comparison, in the scalar tensor theory, this process will happen at a lower frequency. Is that right? Is this thinking right?
Yes, probably so this effect come really because you have this this time varying dipole moment that is absent in GR. So yes, the tidal effects are important usually closer to the merger. So in scalar tensor, they still would be mostly the scalar tidal effect will also be mostly important closer to the merger. I didn't put numbers, but probably they will become more important. Yes. No, actually, I looked at the number. I don't remember. For at smaller frequencies. So it depends a bit on the, okay, sorry, you're right. It will be, so for example, they are more, in the LISA band, they are more important than in the LIGO band. Because it's at a lower frequency. So it's a ratio between the frequency and the scalar charge also. So you need to have, so it's really linked at the difference of between the scalar charge of the two objects. So you need to have strongly scalarized objects to see a difference. So it's a computation between the frequency. So you need to have low frequency and also a scalarized object, differently scalarized object. And in practice, you will see them earlier.
Thanks. Okay, thanks. And we have a question from Shaurya. You can go ahead.
Yeah, thanks, Parami. Thanks, Laura, for the very interesting talk. I'm glad you mentioned that about the potential modifications of GR as alternates to dark matter and the cosmological constant. Now, because we still don't know if dark matter exists in the sense like what the constituents which are actually made up of, right? The fact remains. However, it's often said that dark matter evidences in, say, CMBR and say, let's say, bullet cluster and that kind of thing, they're like smoking guns for dark matter. I'm not saying I necessarily agree, but that's kind of the thinking which is often stated. So if the modifications that you suggest along those lines, will they be able to explain away those things as well without dark matter, like, say, CMBR observations or, say, the bullet cluster observations? I hope my question makes sense. Thank you.
I cannot answer for sure at your question. I'm not a specialist of cosmological. I know that so all those modifications, they try at least to explain for dark matter. The honest answer is I don't know. What I know is that some people have tried to use those theory in particular, and for example, I know for massive gravity or bimetric gravity to use it to explain for dark matter, also at these cosmological probes of dark matter. But I'm not aware of many works on those lines for modified gravity for dark matter. I mentioned it, but yeah, I don't know. I think what usually what is done is that they are studied and used for the dark energy and alternative to dark energy mostly. And in that case, there have been some cosmological simulation in implementing the modification coming from scalar field, for example.
Thank you.
Okay, so one last question we have in chat. Laura, can you see the chat or should I read it?
Yes, I can see the chat. Alors, question about EOB models. Alors, EOB models, usually they use results from PN theory, but they resum and to allow for a validity up to merger, and then there is still a matching. There is no matching with numerical relativity, but there is calibration with numerical relativity. So I think we still need both, even for EOB models, to have EOB models, and it's true also for phenomenological models. And I know that people are working on it, so very soon I think that we will be also have full IMR models, either with EOB or phenomenological model in these scalar tensor theories. The second question about renormalization, well, yes, that's true that like yeah, well, yes, scalar tensor theory with a potential term, it's equivalent to that of our gravity, so they can be mapped, result can be mapped. And yes, it can help for normalization, and it's why also this scalar, this kind of theories with higher curvature to higher coupling to higher curvature are usually introduced to explain this renormalization problem of GR. I don't know if it
thanks.
answers the question.
I think we are over the hour, so thanks to both the speakers, and this brings the first session to close. Now I will hand over to the organizers.
Thank you, Paulavi. Thanks to both the speakers. And the audience, of course, for being here. We'll resume in 10 minutes, which would be 5:15